Okay, good morning, everybody. Thanks, Peter, for the link in terms of geochemistry. From the more remote technology, now we bring it down to Earth. We are now talking about a surface-based exploration tool, if you will, our derisking tool called Amplified Geochemical Imaging. That's what I'm trying to cover this morning. First, give you an idea what GORE, the GORE enterprise, is about. Some of you might have heard about us. Then giving you a bit of an insight to what we are working with in terms of the signal, in terms of the processes, how we work the data, how we do the interpretation, and if time allows, just having two quick views at a couple of case studies, and of course the track record success rates, as these has been already discussed for the other technology before. GORE is a global enterprise, and I guess most of you will have been in touch or are in touch physically even with a GORE piece of equipment, the GORE-TEX membrane. That's one part of the business that GORE does globally. That's this fabrics part over there. But GORE mainly is an industrial products provider. GORE started 50 years ago. And these days, the global enterprise is based on 4 divisions, which is electronics, industrial products, medical, and those fabrics. GORE is driven by innovation that runs through everything we do, and so through our technology as well. Us, which is the GORE Survey Products Group, we are headquartered in Elkton, Maryland, United States. That's where GORE has its enterprise headquarters, so we are not in Houston or somewhere else where we'll be closer to the oil and gas patch. In Elkton, that's where we are manufacturing our sampling devices, which you will learn about in a minute. That's where we have our own laboratory. That's where we do most of the data interpretation and do the sales for the Americas, Southeast Asia, and Australia. From the Munich office, which is the European, GORE's European headquarter, we are mainly serving Europe as a sales territory, former Soviet Union, Africa, and parts of the Middle East. These are a couple of bullet points what our service is about. Obviously, we're talking geochemistry. It's a surface-based method we're dealing with. It's passive, but it's a direct hydrocarbon indicator. So other than remote sensing, for example, we are directly looking for those hydrocarbon, we are capturing them. We are doing this with a great sensitivity. So the signal we are dealing with is on the nanogram scale. To do this, we have our own proprietary sampling device called a GORE module, and you will also learn a little bit about what this does and why it's so special. And the data we are collecting, this very sensitive database then, is interpreted. In different ways, we are throwing a lot of math and statistics at this data to, in the end, being able to provide probability values for hydrocarbons being present in the subsurface. So how could an oil company or oil and gas company benefit from what we are doing? There are basically 3 steps of a workflow where we could help. First, it's a frontier stage when it's about validating the petroleum system, telling you is the block prospective at all, helping you screening the block so that you could put the seismic where we see prospectivity. The next little bit later on step is when you have mapped already those prospects from the seismic data and you would like to assess charge for those individual prospects. Or even a later stage when you're in the development phase or even production phase, when you have a decreasing production rate from this area, we could help you looking for bypass pay. All this is done on and offshore. And just to give you one quick view at how the data could be used, this is an area, assume this is top reservoir map we're looking at, where you have those 3 structures mapped, and assume they all look equally tempting for you to drill. We could come in, provide our data layer, and what you're seeing here is probability values for those hydrocarbons being present in the subsurface. The warm colors stand for high probabilities, the colder, the blue colors for lower probability values. And by adding this data on top of the structural data, we are able to highlight those areas which we would then recommend for further attention. In this case, we certainly highlighted this structure down here in the south. We didn't see any prospectivity up here. We saw some prospectivity here. So in our recommendation to the client, we would say best chances down here, second there, and don't look any further since we don't see much of a prospectivity there. In this case, the data got drilled up, fortunately, and proved our statements in terms of prospectivity, where we had shown the maximum prospectivity. This turned out to be an oil well. In this area, which got drilled up, it turned out to be a dry well. The data we are collecting at the surface is delivered to the surface by a vertical migration of hydrocarbons. And I'm pretty sure that everybody is familiar with the process called macro seepage. So migration of hydrocarbons along fractures, along faults, discontinuities up to the surface. In this cartoon, this is indicated by those yellow arrows. Can you see the point? No, it is. Okay, there. That's a fault line. It's a reservoir down here. You have you get those hydrocarbons delivered to the surface. Those create those macro seeps that you see either onshore or offshore in corresponding features. Well, that's a process we can work with, but we rarely work with. So that's a process where you have hydrocarbons in detectable and visible amounts at the surface, where you have this pathway, those faults, where those hydrocarbons migrate through. But this pathway and correspondingly the point where you actually see those macro seep at the surface is usually offset from the subsurface source. So it's good when you find macro seeps to validate your petroleum system. It's not very good if you actually want to map charge for a reservoir. The good thing is that there's this other process called micro seepage out there. And micro seepage is a strictly vertically acting process indicated by those red and blue arrows. So from the reservoir, you would have hydrocarbons migrating to the surface, driven by pressure in the reservoir. And as you can see here, we have kind of two families of arrows. We have the red ones, which stand for the real micro seepage signal from the reservoir, contrasting the blue ones, which is background signal. In this case, by detecting the signal at the surface, we are able to map the signal in the 2D view and help you identifying those prospective areas. At the same time, it's clear that in such a setting, we'll always have to differentiate what's the real signal from what's the background signal. And just a very quick look at the mechanisms which could be or which seem to be responsible for this process. What's favored at the moment is a process called microbuoyancy that delivers those hydrocarbons at surface. And microbuoyancy means you have micro bubbles of hydrocarbons. And we are talking Unström size, so very tiny bubbles, which are small enough to use grain boundaries and microfractures in the rock to arrive at the surface, driven by pressure, driven by buoyancy. That's the reason why this process occurs in pretty much every type of lithology. So there is, for the micro seepage process, there is no barrier in terms of salt, crystalline rock. Also, there is no deflection, at least not visible for us, in terms of strong groundwater currents, for example. There is more information on this, and if you are interested, dive into this APG Memoir 66. Klusman et al. Have compiled this in the year 2000. That gives you a good status report on how science views this process at the moment. What's important for us, and one strength certainly of our method, is the way how we're collecting the signal. And that's where GORE comes into play, and that's where we are connecting with GORE Fabric. What we're using is a GORE module, and the GORE module is basically a tube of GORE membrane. It's very similar to a GORE-TEX membrane. And those of you who have a piece of garment of GORE, you hopefully experience that it's waterproof, at the same time vapor permeable. So we use those properties to package up our adsorbents, our chemical adsorbents which are inside of this, or which are kept inside of this tube, and those are specifically designed to capture hydrocarbons. We have two of them, one to capture the lighter ends, one to capture the heavier ends hydrocarbons. That means for us that we are able to capture hydrocarbons up to the C20 range. Conventional surface geochemistry collects C1 to C5. So we are able to extend into the broad bandwidth of those thermogenic compounds, which are important to discriminate between oil and gas, for example, in our signal. It's a time-integrated sampling. That means that onshore, this module is put into the ground and it stays there for about 3 weeks of time. And since we are focusing onshore today more than offshore, in the onshore environment, you would create a hole about 0.5 meter deep and 1 centimeter in diameter. You would insert this module into this hole, close it, mark the location on the GPS, and keep going to the next sampling point. After 3 weeks' time, you come back, you retrieve the module, and once the survey is done, those modules are shipped back to our laboratory in the United States. Offshore, the sampling approach varies with the scope of work and varies with terrain. And these days, we have a broad offering to match different needs out there. I don't have the time today to go through all those. I just want to highlight one thing, which is our slick sampling up there. And this is, since it varies a little or differs a little bit from the other approaches we take, where we are able to use a little bit different adsorbent-based sampler to sample those surface slicks. What you do is you cast the slick sampler overboard, basically, drag it through the slick for 2 minutes, put it back into our sampling jar, and you are able to analyze the signal. Here we are able to analyze compounds from C5 up to C35. So we are able to extend into those biomarker range, which is important when we talk about maturity, source rock composition, and so forth. What we do in a joint effort, I would say, with our colleagues from Astrium, former Infoterra, is to come up with a system that's called a near real-time slick mapping and sampling. So where we're using remote data, satellite data, the global SEEPS database from Astrium, to identify those slicks and then use our sampling capability to go out there and sample those. As one example on where we can come in very, very early. Slick sampling is done very early in a process where you really want to validate your petroleum system. In the standard offshore application, we would use seabed sediment. And those seabed sediments are collected usually by coring to the deck of the vessel. And on deck, you would subcrop from the deepest part of the core about 100 cubic centimeters into the jar. And then you would add our offshore module that looks a little bit different from this one into this jar, close the lid, put it on the shelf, and keep it there. Again, it's a 3 weeks exposure time, sediment to GORE module. So after those 3 weeks, you take the modules out of the sediment and run the similar analysis as you would do onshore. The survey design we are working on has to correspond to the scope of work. So starting from a frontier application where you might space those samples 2 kilometers apart, down to a high resolution survey where you want to actually map hydrocarbons in a given structure, where it comes down to 250 meter spacing, maybe even 200 meter spacing. In an ideal world, we like to work on grids, since grids are statistically unbiased. At the same time, they allow, or the data we generate from grids allow for full 2D integration with the existing GNG. But this might be reduced to triple or double line transacts if areas get very big and the number of samples would increase extremely. When those samples, when those GORE modules come back to our laboratory, they undergo an analytical workflow from thermal desorption, where we are driving those hydrocarbons off our adsorbents, run through GCMS, basically a standard approach for analysis. And what we are dealing with and what we are focusing on are 87 compounds. So that's a wealth of compounds we are looking at. And I have no intention to go into this in detail right now, but just to show you that this upper tier is basically what you would go after if you do normal petroleum geochemistry. We add a range of compounds down here, which are byproducts and alteration products. And those are in there because the signal we are dealing with is not the live oil or the live gas you get right from the well. We are dealing with the expression of the signal at surface level after this hydrocarbon signal has migrated through kilometers of rock. And on this journey through the rock, the signal has been altered. And this alteration effect is something we want to capture. We need to capture, especially when we want to make a good differentiation between what's background and what's the real signal. That's why they're in there. When we do data interpretation, what we're always after is the enhancement of the signal to noise so that we are really able to tell apart what's the real hydrocarbon signature we're looking for and then what's background. So QA/QC for us is a very important aspect of our work. And there are several measures to make sure that the data we are working with is actually fit to use and is real data that only is portraying the hydrocarbon, the petroleum situation in an area, and might not be affected by contamination or other effects, other artifacts. To show you how our data looks like, this is what we call a geochemical signature recorded around an existing well. So we have taken 15 of those samplers here, put them around an existing well, and created this average geochemical signature. So what is it? The baseline here gives you hydrocarbon compounds from the C2 up to the C15 in this case. What you also do see is what I would call a classy thermogenic peak for an oil. You see the specks of the oil down here. What we also try to highlight on this slide is the range of compounds you would usually look at when you do conventional surface-based geochemistry, which is C1 up to C5. So this being recorded around an oil well. This one has been recorded, again with those 15 modules, around a dry well. And you see that, especially when you extend into this range of compounds, there's not much there. That's what you kind of would expect from a dry well, right? But when you look at those light end compounds, C2 to C5, they look pretty similar to what the oil looks like. So our bottom line here is certainly if you restrict yourself and only look at those light end hydrocarbons and try to come to grips on the prospectivity, you might not be accurate. Since dry, so background or negative and positive might look very similar. This is a geochemical signature recorded around an existing gas well, just to show you how this might look like in our data set. And interesting on this slide is that this is a very dry gas, so it's a 99% methane gas, where we are not measuring methane at all. So this one volume percent of this gas being non-methane, giving our high sensitivity was enough to develop the full hydrocarbon signature for this petroleum. When we record our data and do the basic interpretation, we get to a point where we have a very rich, comprehensive geochemical data set, and you could run whatever type of analysis you would like to do with it. You could cross-plot pristine phytane or do other things with it. But when we try to make the next step then, based on this data set, which is our geochemical modeling approach. And for this geochemical modeling, we have basically two ways of approaching it. One, in an area where we do have well control, we would use those existing wells as calibration points. So we would actually do what I just have described. We take those 15 samplers, put them around an existing well, and take this hydrocarbon information to create those maybe the battery is low on this. Okay. We create those average geochemical signatures for an oil, in this case for a dry, and for a gas, since we had two petroleum phases in the system. Each individual data point then that we collect, and those blue dots stand for all those samples that have been put into the ground, each data set will be analyzed, a geochemical signature will be created, and this geochemical signature then is compared in terms of its geochemical pattern with those end members, the positive one, oil or gas, versus the negative one. And if you will, the degree of similarity, of the geochemical similarity based on the pattern, is then expressed in a probability value. That means in an area where we say there's a high probability for finding hydrocarbons, in that area the geochemical signature of the individual data point is very similar to what we have defined as the positive end member. When we give you a low probability value, that means that the geochemical signature is very similar to what has been defined as the dry end member. This comparison is done based on linear discriminant analysis. So it's a statistical tool that does this comparison to the probability value. In an area where we do not have the well control, we are applying a different approach to the data. And this data, or this approach, is called cluster analysis. So cluster analysis basically looks for similarities in data sets. This has nothing to do with geochemistry at all. You can cluster whatever type of data set you would like to go after. In our case, though, we look for similarities based on the geochemical target compounds we're dealing with. And the result of a cluster analysis is conventionally what's called a dendrogram. And on this, you would have all the data points, so all our GORE modules that have been involved in the survey on the y-axis. And on the x-axis, we're looking at those geochemical compounds that have survived our signal-to-noise process. So those compounds between the C2 and the C20. Degree of similarity in between those data points is expressed by red color on this plot. So you can right away see, since the software plots those data points together according to similarity, you can right away see where and based on which compounds those data points are similar. So the upper tier gives you information on similarity based on the heavy range compounds. So let's say from the C12 up to the C20. This middle one here is void of any similarity values. And then we have a low one out here that shows more similarity for the light to mid-range hydrocarbon compounds. That's not geochemistry up to this point. We have to validate what this means. And by looking at it and assuming you have a group of samples who show an imprint for heavier range hydrocarbons, well, this might be related to oil. So what we would do is we create an average geochemical signature for this upper cluster. And this geochemical signature then is used to validate, is this really an oil? Does this look like an oil signal or not? The same for this middle cluster and for the lower one. And what we came up with in this case was clearly an oil cluster, the upper one, the middle one, a background cluster, and the lower one being a cluster for the oil condensate. These pieces of information then are defined as end members. So you take this as the positive end member for an oil, this for a positive end member for a gas condensate, and this for background. And you would apply the same modeling we did before. In the end, what we are delivering is a probability map, at least one. If we would have two end members, an oil and a gas, we would provide at least two maps. Gas versus dry and oil versus dry. And as I explained in the beginning, the warm colors stand for high probability values, the low for lower probability values. This is in case from Egypt through 3.5 kilometers of salt. And this map is, of course, only one part of the final report we would deliver to the client of the deliverable. You see there's much more information in there. We work closely with the clients, especially on the geochemical modeling, to make sure that the models we develop are in accordance with what the client believes the geochemical, the geologic model tells him. And a very important aspect for us is then the integration of the data. Since this is one data layer to derisk the exploration, to de-risk the prospect. Of course, this needs to be applied and needs to be integrated with the existing G&G to become most powerful in the end. Usually there are two questions when we talk to clients about microseepage. One is, can you work through salt? And this is an example that we can. Just one snapshot at a case where we work Egypt, the Dead Sea Rift tectonics, and the reservoir level was below about 3,500 meters salt. So we delivered data for this subsalt play in Egypt. It got drilled up, and in this survey we used 150 modules in a spacing of 200 to 250 meters, which is what we would call a high resolution approach, a high resolution type survey. When you look at the tectonics, we were pretty much spot on with our positive anomalies and how they lined up with the existing rift tectonics, the Horst and Graben structures there. The next question we usually get would be, can you work with multiple reservoirs, with a stacked reservoir situation? Yes, we can. And that's an example from the Wilcox Basin in Texas, where we worked through the shallow gas and delivered data for this Wilcox gas that has been proven up later on by 3 wells on the Wilcox. So even if we are recording a surface signal, and even if the signal contains 2 fractions, in this case the Wilcox fraction and the shallow gas fraction, if we have a way to model the data properly, we're able to tell those apart and only focus in, zoom in to one reservoir that's of interest. To wrap up, why do we believe we have an advanced tool for the de-risking out there? And to do this, we have 2 universes. We have the geological universe on the left and the hydrocarbon universe at the base. On the geological universe, we believe we are advanced because we can work in pretty much every type of lithology that's out there. We are able to work in drier or wetter conditions because our GORE module is protected. On the hydrocarbon compound universe, we offer data from the C2 up to C20, and we are not restricted to where soil gas is usually operating, C1 to C5, operating under restricted boundary conditions when it comes to lithology and wetness. Our great sensitivity is certainly a major benefit of our data. We are not dealing with methane, since methane from our point of view would always require that you distinguish between what's biogenic and thermogenic in this data. So it basically asks for isotopic analysis. So we skip methane, we focus on this broad range of compounds that's beyond. The track record for us, we are in the market for about 15 years, 18 years now. We've carried out more than 600 surveys. You can see for how many companies and countries we worked. The good thing is really our flexibility when it comes to terrain. So from desert to permafrost soil, this is applicable. Even swampy areas or shallow marine areas, if we talk onshore. Our success rate is at about 90%. And what this means is, with our internal database, at the moment we have about 180 wells recorded that have been drilled on our data. And when we look at our oil and gas prediction, at the moment we are at about 93%. So in 93% of cases, when those positive anomalies have been drilled up, that client actually found hydrocarbon. On the negative end, if we predicted dry, and if these have been drilled up, at the moment we're at 92%. With the positive prediction, there's still some ambiguity to the data though. since we cannot tell you at which depth or which volume. So that for clients, it might be even more interesting to look at the negative, at our dry well prediction, especially when you try to sort out prospects for the drill bit. With this said, thank you very much for your interest.
Thank you, Dirk. Any questions? Everybody clear? What's one over there, please?
Thanks. Actually, two questions. What is the spacing typically between your sample taking? And second question, can you give us some indication of costs, please?
The sample spacing ranges between 200 meters and 2 kilometers. It really depends on the scope of work, on the objective. And the close spacing is something we would apply in a high resolution survey. So if we would like to assess charge within one definite structure, if we would be out there even to find oil-water contacts, for example, then this would be 200 meters. If we're screening a large block, it might be up to 2 kilometers further apart. Cost, there are two parts in it. One is certainly our geochemistry, the analysis, survey design, and so forth. The other would be fieldwork. So leaving fieldwork alone for the moment, ballpark figure for an onshore sample, 1 point is about $500. So giving minimum survey size of 150 points, this is kind of the minimum amount of money you're looking at for the geochem, plus the fieldwork.
Thank you. Okay, anybody else? Okay, no, thanks. Thank you, Dirk. Thank you for that.